So in this video, I'm going to work through and give you some pointers on the formula of Hydrates lab. And so it's important to realize what a hydrate is. So when an ionic compound forms, it's going to form a crystal, and sometimes as it's forming, water will get trapped within that crystal. And so we have an ionic compound, and inside that are water molecules. And what we do is when we write the formula for that compound, here's the formula for our ionic compound, and then we put a dot there. It's like what we call a centered dot. It's on the middle of the row, followed by the number of water molecules that are trapped in the crystal for every unit of our ionic compound. So you can see in the introduction, there's a whole series of examples of how you write the formula of a hydrate. And there's also a section in your book about writing the formulas of hydrates as well, so you can look up that information if you want to. Now, when an ionic compound forms and it either doesn't have any water trapped in the crystal, or alternatively, if it forms as a hydrate and then we remove the water, we call that the anhydrous compound. That means without water. So an anhydrous ionic compound doesn't have any water with it, and then a hydrate will have some water. So that's a hydrate, okay? Now, it turns out that if we have a hydrate and we heat it up, it will lose the water. And we're going to do this for two different hydrates in this lab. We're going to take some zinc sulfate hydrate. That's a solid. We're going to heat it, and that's going to give us solid anhydrous zinc sulfate, and then X moles of water will leave as a gas. So obviously our solid has lost some matter, has lost mass, so our anhydrous compound, this guy at the bottom here, will weigh less than our hydrate. And from the difference in mass between our hydrate and our anhydrous compound, we can calculate the mass of water that was lost. So that's explained in the introduction as well. Here it is in 1.1. Now the example that's given throughout the introduction is for calcium chloride rather than for zinc sulfate or copper sulfate like what we're going to be looking at. But the math is exactly the same. And what we're trying to figure out here for both of our cases of a copper sulfate hydrate and a zinc sulfate hydrate is what is the number of water molecules for every unit of our ionic compound. So there's a section in the introduction that explains clearly how to do this. The first thing we're going to do is to calculate the mass of water that was lost. And that's not that difficult. You take the mass of the hydrate, and from that you subtract the mass of the anhydrous compound. And then what we're going to do is we're going to convert that mass of water into moles. And that's pretty easy. You just take the grams of water that was lost and divide it by the molar mass of water, which is 18.02 grams per mole. Now in our case, what we're going to do is we're not going to take the moles of calcium chloride, we're going to take the moles of whatever our anhydrous compound happens to be. So it's going to be either zinc sulfate or it's going to be copper sulfate. But the math we do through here is exactly the same. So we take the grams of our anhydrous compound, either our zinc sulfate or our copper sulfate, divide that by its molar mass, which you can compute using an online molar mass calculator, and we will get the moles of our anhydrous compound. And then it's a pretty simple process to get your X, your number of moles of water for every mole of your compound. You just take your moles of your water and you divide it by the moles of your anhydrous compound, which you just calculated. So we're going to do that a total of 4 times. 2 times for the zinc sulfate and 2 times for the copper sulfate. So in this lab, what happened is that we took a small amount of each hydrate and we put it into a crucible, which is a porcelain or ceramic dish that it's possible to heat really hard. And then we heated that using a Bunsen burner, and a Bunsen burner heats up to about 1500 degrees Celsius, which is well above the boiling point of water. So all of the water will leave as steam and the mass will go down. So the data that you're given is it gives you the mass of the empty crucible and then the mass of the crucible with the hydrate in it. So you can see that we're using a little bit over 5 grams of the material. So, you know, if we just take the mass of the hydrate and the crucible, and then we can subtract from that the mass of the crucible, well, you can see what we're left with is the mass of the hydrate. And we're going to use that, we're going to then turn that into moles, right? So you're going to do that little procedure again. You've always got your sample, whether it's the anhydrous sample or the hydrated sample, with the crucible, and in each case you're going to have to subtract away the mass of the crucible. Now, once you've got your mass of hydrate and mass of anhydrous compound, you can go back and calculate, just using this little formula, the mass of the water. And at that point, you're ready to go on and do all of your moles calculations. So it's not too hard. Just fill in that table. Make sure you keep your significant figures straight. All of your masses need to go out to 3 decimal places. And then when you start multiplying and dividing, you're going to have to apply your rules for significant figures. At the very end, you're asked to give the formula of the hydrate, and remember that this should be of the form where you write the formula of the ionic compound, a center dot, and then a number followed by the formula of water. So don't write something else other than that. That's not how we write the formulas of hydrates. We've got to write it in that form. So you're going to get 2 of those, and hopefully they're close to one another. All right. So then we're going to do the same for a zinc sulfate hydrate. And again, hopefully your 2 repeats are somewhat near one another. So you're asked to provide a set of calculations for each compound. So 1 example calculation all the way through for each compound, right? So 2 example calculations from the beginning to the end. You're then asked to kind of like think about what might happen if you didn't heat your sample long enough. How would that affect your masses, and then overall, how would that affect your formula? So I always kind of prompt people when you're answering a question like this, look for the question marks, right? And then it says explain, so you need to be very deliberate in how you explain. So you want to make sure you answer all of the parts of the question and also give an explanation as to how you arrived at your answer. Okay, so in this part we have to write a method section, and a key thing about a method section is that it is in past tense. So that's different from how you might have seen people like write a recipe. If you get a recipe book, a cooking book, it says something like, you know, take whatever, and then it's telling you to do things, right? Do this, right? Blah, 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 blah. Mix this. So it's like something that you're doing at that point in time. Whereas when you read a method section written by a scientist, it will say, we, you know, baked. It's all in the past tense. We mixed whatever might be going on. It's like describing an experiment that has already been done. So it is not a list of instructions for something that's going to be done in the future. It's a narrative written in past tense. So a narrative means that it's not a bulleted list. It's not a numbered list, right? It's sentences, right? One after the other, describing something that has already been done. The aim is that you kind of keep it brief, but you don't leave any details out, which is kind of contradictory. But generally scientists don't like reading a lot of stuff. They want you to be kind of blunt and to the point. And then the other thing is that it's important that you include all amounts and identities of substances, and also the length of time that you carry things out for. Now, the length of time, it doesn't have to be like, you know, so many hours and so many minutes. It can be like until, right? You know, it could be like, you know, things were mixed until they were at a consistency of something or other, right? So it doesn't have to be necessarily a measure in hours and minutes when you're talking about time, but you need to be very clear on the identity of things, and you also need to be very clear on the amount of things, because the idea is that somebody could use your procedure to repeat your experiment, and if you don't have identities and amounts and times of things, then that's not going to happen. So in this case, keeping all of these things in mind, this is how I would begin. He's going to say this: two samples of zinc sulfate hydrate were heated in, I should point out here, we should do the masses, so we know what the masses of those two samples are. Were heated in a crucible until dry, then reweighed. From this data, the formula of the hydrate was determined. Boom. And then you can say this process was then repeated with two samples of copper sulfate hydrate, and again give the masses. So it's pretty simple, right? Two samples of zinc sulfate hydrate, and you give their masses, were heated in a crucible until dry, then reweighed. From this data, the formula of the hydrate was determined. This process was then repeated with two samples of copper sulfate hydrate, and again I give the masses. So I think that works great. I think that that's a classic sort of like, brief but complete. It's in the past tense. It gives the identity and the amounts of everything. It tells you how long things were heated for until they were dry. So you'd heat them until there was no more obvious water coming off, right? Until, they were clearly dry powder. It tells you everything you need to repeat this experiment, but it doesn't add sort of unnecessary detail. So I think that's great. That's where I would begin with this. You might have a difference of opinion on that, but I think that that's a good example of a procedure. Okay, so let's move on to the next question. Now, the next question is about writing a discussion for a lab, which is definitely probably something that you haven't done before, at least in the chemistry lab. So let's see what we've got. So it says, not a discussion, a conclusion. It says, often scientists will conclude a scientific paper with a summary of their key findings. Now, if we think about this, what are our key findings for this experiment? They're going to be our formulas, right? And then it says suggestions for future work. So, maybe, like what could you, future work. That's something to keep in mind. And then it says, write a conclusion which you discuss key results, errors, and potential improvements. Okay, so we don't have to worry about future work. That's just like an example of what you could include. So the three things that we are asked to write a conclusion about are key results, which we said was our formulas, errors, systematic and random, and we need to talk about what those things mean, and then random, And then finally, potential improvements. Okay, improvements. So let's talk about the key results. The key results is the formulas. So you want a sentence that gives the formulas. And so I would just say something like this. The formulas of the hydrates were found to be, and then I would give your two formulas. Alright, so that would cover your key results. Now for your error, you're asked to discuss whether you've got systematic or random errors. Now we're talking about errors in terms of statistical errors. These are not like, errors are not like, they're not like mistakes. These are things like you were trying hard, you were doing everything how you were meant to be doing them, but stuff still is not perfect. Because if you make mistakes in the science lab, you don't report your results, you go back and do the experiment again. So you shouldn't be saying things like, oh, I would be more careful. That's not right. So systematic errors, what are those? They are errors that cause everything to be too big or too small in a systematic way. So what do we mean by bigger than what or smaller than what? And what we really want to be doing here is looking at accepted values. So you want to do a Google search for copper sulfate hydrate and see what the accepted values are for copper sulfate hydrate, what most people report. You want to look at zinc sulfate hydrate and see what most people report for that. And then see if your values are like consistently too big or too small in comparison to the generally accepted values. Now, random error is when here's your true value and your values are kind of scattered. Some are too big, some are too small, right? Now, we're not really going to be able to tell that that well when we only have two measurements. But what we're really going to comment on here is, are our results scattered or are they near one another? So it's really kind of like the precision of our measurements, right? Are the repeats of our measurements close? Right, that's what I would be talking about there as far as random error is concerned. Our measurements, is it repeatable or are there big differences between the two repeats? Now, for potential improvements, I think there's like quite a few. One is that, you could simply do more repeats. Right, that would be one. Something else that I was thinking about is we just heated this until dry. Is there a procedure you can think of that you could introduce to confirm that they really were dry? Right? And I can think of one. One would be like heat it again and see if the mass continues to go down or whether it stays the same. And if it stays the same, then you really have got it dry. Okay, so I think that would be something that you could talk about. The other thing you could think about is like the size of the sample. If you have a really big sample, we're going to get really big changes in mass when we heat this up. So we could think about sample size because it's going to be, you're going to be able to measure bigger changes with greater precision. So that would be something that you could consider. So there's at least three that you could think of for improvements here, and it'd be nice if you could come up with some by yourself. So that's really the lab. There's only the 4 questions there, I think, and the first one is just showing your work. Remember, you've got an example calculation up here for calcium chloride, and you just got to follow that through for your 2 examples, and you'll be fine. Yeah, a set of calculations, and then you're going to do a reflection upon what would happen if a certain sort of mistake was made. How would that affect your results? And then we're going to do the method section, which I basically gave you, and then you're going to write the conclusion. And as long as you hit all of the points that you're asked for there, then you're probably going to get good scores for your conclusion as well. Alright, so that brings this video to an end, and I hope you found it helpful.